Welcome to this walkthrough of LeetCode problem number 1902, depth of BST given insertion order. In this session, we'll explore how to compute the depth of a binary search tree created from a given insertion order. We'll break down the problem, analyze the approach, and consider the complexities involved. Let's dive in. In this problem, you are tasked with constructing a binary search tree, or BST, from a given array called order. This array specifies the sequence in which the elements are inserted into the BST. Now, a BST is a tree structure where every node follows specific rules. The left subtree of any node contains only values that are smaller than the node's value, and the right subtree contains only values that are larger. Furthermore, these rules apply recursively to the left and right subtrees as well. Once the tree is constructed, we calculate the depth of the BST, which is defined as the maximum number of edges along the path from the root node to any other node in the tree. For our purposes, the root node starts at depth 0. The goal is to compute and return the depth of the BST after inserting all elements from the order array. The input to the problem is an integer array called order. This array has a length n where n can range from 1 to 10,000. Each value in the array is guaranteed to be unique and lies between 1 and 100,000. The order of the elements in this array determines the sequence of inserts into the BST. The output is a single integer, which represents the depth of the BST that results from this insertion process. To clarify how this works, let's look at some examples to understand how the tree is built and how the depth is calculated. Here's the first example. The input array is 2, 1, 4, 3. Starting with the first element, 2 becomes the root node of the tree, and since it's the root, its depth is 0. Next, 1 is inserted, and because it's less than 2, it becomes the left child of 2, with a depth of 1. Then, 4 is inserted. Since it's greater than 2, it becomes the right child of 2, also at depth 1. Finally, 3 is inserted. It's less than 4 but greater than 2, so it becomes the left child of 4 at depth 2. The maximum depth among all nodes in this BST is 2, which is the output. Now let's consider a second example where the input array is 1, 2, 3, 4. Here, we start with 1 as the root node, so its depth is 0. The next element, 2, is greater than 1, so it becomes the right child of 1 at depth 1. Then, 3 is inserted. Since it's greater than 2, it becomes the right child of 2 at depth 2. Finally, 4 is inserted and becomes the right child of 3 at depth 3. Notice how this forms a skewed tree, where all nodes are in the right subtree. The maximum depth of this BST is 3, which is our answer. For the third example, the input array is 5, 3, 8, 2, 4, 7, 9. First, 5 becomes the root node at depth 0. Next, 3 is inserted to the left of 5 at depth 1, and 8 is inserted to the right of 5, also at depth 1. Then, 2 is inserted to the left of 3 at depth 2, and 4 is inserted to the right of 3, also at depth 2. Similarly, 7 is inserted to the left of 8 at depth 2, and 9 is inserted to the right of 8, also at depth 2. In this case, the tree is more balanced, and the maximum depth of the BST is 2, which is the output. There are a few constraints and edge cases to consider for this problem. First, the length of the order array can range from 1 to 10,000, and all values in the array are unique and fall between 1 and 100,000. For edge cases, if the array contains just one element, the BST will consist of a single root node, so the depth is 0. For a sorted array, the BST becomes a skewed tree, and the depth will equal n1. On the other hand, a balanced insertion order results in a tree with minimal depth. Finally, for large inputs, the solution must be efficient in both time and space to handle up to 10,000 elements while still constructing the BST and calculating its depth correctly. To tackle the problem of calculating the depth of a binary search tree, or BST, based on a given insertion order, we need an approach that efficiently simulates the BST construction while tracking its maximum depth. The first method we could consider is a brute force approach, which involves simulating the full tree construction. Starting with an empty tree, each element from the input array is inserted one at a time. For each insertion, we find the correct position in the tree by traversing from the root, comparing values, and placing the node appropriately. While this approach is straightforward and uses a tree node class to represent the structure, it becomes computationally expensive. In the worst-case scenario, such as a sorted input, each insertion could require traversing the entire depth of the tree, leading to an overall complexity of O(n) squared. This makes it impractical for large inputs. An alternative is the optimized approach, which avoids explicitly constructing the tree. Instead, it simulates the insertion process using a range-based binary search. By maintaining a list of ranges that represent the BST structure, we can determine the depth of a node based on comparisons with these ranges. This observation significantly reduces the computational effort while avoiding the overhead of managing a full tree structure. With the range-based simulation, every insertion splits the current range into left and right subranges, and the depth of the inserted node is simply the number of divisions or levels required during this process. To implement this, we use a helper function that tracks the depth dynamically as we process each element, updating the range boundaries accordingly. This approach achieves a time complexity of O(n), as each element's insertion and range adjustments are performed in constant time. The trade-off with this method is that we lose the explicit tree structure, which may make the process less intuitive at first glance, but it compensates with its significant speed advantage. Another alternative is to use a Fenwick tree or segment tree to maintain counts of elements at each depth level in the BST. These structures allow us to update the tree efficiently as elements are inserted and to query the depth as needed. However, while this method offers a complexity of O(n) log n, the additional layer of complexity in managing these data structures makes it less appealing for this particular problem. After evaluating our options, the optimized approach with range-based simulation emerges as the ideal choice. It combines efficiency, simplicity, and scalability, achieving a linear time complexity of O(n). This makes it well-suited for handling large inputs, including edge cases such as sorted or reverse-sorted arrays. Unlike the Fenwick tree or segment tree methods, which are more complex to implement, the range-based simulation is straightforward and easy to understand. A key insight here is recognizing that the depth of a node depends solely on the number of divisions required during its insertion, rather than the explicit structure of the tree. This realization, or aha moment, allows us to bypass the need for a physical tree altogether, focusing instead on the range dynamics to calculate depth sufficiently. While the optimized approach is highly efficient, it comes with the trade-off of not producing an explicit BST structure. This is a reasonable compromise, as the problem only requires us to calculate the depth and not construct the tree itself. The Fenwick tree or segment tree alternative, though efficient, introduces unnecessary complexity for a problem that can be solved in O(n) time with range-based simulation. In conclusion, the range-based simulation offers the best combination of simplicity, speed, and clarity, making it the preferred solution for this problem. It achieves the goal with minimal overhead while maintaining scalability and accuracy, striking a perfect balance for this computational challenge. In this problem, we are tasked with calculating the depth of a binary search tree, or BST, based on a given insertion order provided as an array. The depth refers to the number of edges along the longest path from the root node to any leaf node. To solve the problem efficiently, we need to simulate the BST construction step by step and track the maximum depth dynamically as we insert each node. The process begins by initializing the tree structure, where we use a helper class called TreeNode to represent each node. Each node will store its value and references to its left and right children, which are initially set to none. At the start, the tree is empty, so the root is set to none. From there, we insert nodes one by one from the array order, following the standard rules of BST insertion. When inserting nodes into the BST, the first step is to check if the root is none. If it is, we create a new tree node with the value of the first element in the array and set it as the root. Since this is a single node tree, its depth is 1. For subsequent elements, we traverse the tree to find the correct position for each new node. If the value being inserted is smaller than the current node's value, we move to the left child. If it's larger, we move to the right child. The new node is inserted when we encounter a none position on either the left or right. During this traversal, we keep track of the depth of the current node being inserted using a variable called current_depth. This variable is incremented each time we move down a level in the tree. If the current_depth exceeds the previously recorded maximum depth, we update the max_depth. Special cases include an empty array, where the depth is 0, and arrays with all identical elements, where the depth remains 1. For sorted arrays, the tree becomes skewed, resulting in a depth equal to the length of the array. Finally, after all nodes are inserted, the max_depth is returned. The BST's properties are critical to the algorithm because they ensure that each value has a unique path for insertion. Smaller values always go to the left, and larger values go to the right, which dictates the structure of the tree. The depth of the tree increases as we move downward during the insertion process, and the maximum depth is updated whenever a node is placed deeper than the previous maximum. Analyzing the time complexity, in the worst-case scenario of a completely skewed tree, each insertion takes n operations, where n is the number of nodes. For a balanced tree, the insertion time is reduced to O log n. The total time complexity for processing all nodes depends on the tree's structure, ranging from O(n) to O(n log n). The space complexity is straightforward, as each node in the BST occupies constant space, leading to a total space requirement of O(n). To implement this algorithm, we use two primary data structures, the treeNode class and a few supporting variables. The treeNode class represents each node in the BST and contains fields for the node's value, left child and right child. The root variable serves as a reference to the tree's root node, while max_depth keeps track of the maximum depth encountered during the insertion process. Another variable, current_depth, is used to monitor the depth of each node as it is being inserted. The key operations include the insert operation, where we traverse the tree using the BST rules to find the correct position for the new node. Once the node is inserted, we update the depth dynamically. This depth tracking mechanism allows us to efficiently calculate the maximum depth during the tree construction process. The pseudocode for the algorithm begins with the definition of the treeNode class, which initializes a node with a value and sets its left and right children to none. The main function, BST_depth, starts by handling the edge case of an empty input array, returning a depth of 0. If the array is not empty, we initialize the root as none and the max_depth as 0. As we iterate through the elements of the array, we check if the root is none. If it is, we create a new tree node with the current value, assign it to the root, and set the max_depth to 1. If the root is not none, we begin traversing the tree to find the appropriate position for the new node. The traversal starts at the root, with the current_depth initialized to 1. The traversal process continues as we compare the value to be inserted with the value of the current node. If the new value is smaller, we check the left child. If the left child is none, we insert the new node there, update the max_depth if the current depth plus 1 exceeds the previous maximum, and exit the loop. If the left child is not none, we move to the left child and increment the current_depth. Similarly, if the new value is larger than the current node's value, we follow the same process for the right child. This loop ensures that the new node is inserted at the correct position in the BST while dynamically updating the depth information. Once all nodes have been processed, the function returns the max_depth as the final result. To better understand the algorithm, let's walk through an example. Consider the input array order equals 10, 5, 15, 2, 7. The first value, 10, is inserted as the root. Since this is the only node, the tree's depth is 1. Next, we insert 5, which is smaller than 10. Following the BST properties, 5 becomes the left child of 10. The depth of the tree increases to 2 after this insertion. The tree structure now has 10 as the root and 5 as its left child. Now, we insert 15, which is larger than 10. This value becomes the right child of the root. The depth remains 2 because both 5 and 15 are at the same level. Next, we insert 2, which is smaller than both 10 and 5. Following the left child paths, 2 is placed as the left child of 5. This increases the tree's depth to 3, as 2 is now at a deeper level than the previous nodes. The tree structure becomes more complex, with 10 at the root, 5 and 15 as its children, and 2 as the left child of 5. Finally, we insert 7, which is smaller than 10 but larger than 5. This value is placed as the right child of 5. The depth of the tree remains 3, as 7 is at the same level as 2. The final tree structure is well balanced, with 10 as the root, 5 and 15 as its children, and both 2 and 7 as the children of 5. The algorithm outputs a maximum depth of 3, which represents the longest path from the root to a leaf. This approach efficiently calculates the depth of the BST during insertion while handling edge cases like empty arrays or skewed trees. By leveraging the BST properties, we ensure accurate placement of nodes and dynamic depth tracking throughout the process. Here, we begin by defining a class called Solution and its method maxDepthBST, which takes an input order, representing the insertion order of nodes in the binary search tree. Inside this method, we define a helper function insert_n_get_depth to handle the insertion of a value into the BST while simultaneously calculating the depth of the tree at the point of insertion. The function starts with a depth of 0 and enters a loop to traverse the tree. If the value being inserted is less than the current node's value, we check if the left child exists. If not, the value is inserted as the left child, and we return the depth increment by 1. If the left child exists, we move to the left subtree and continue. Similarly, if the value is greater than or equal to the current node's value, we follow the same process for the right child. This ensures that the tree is built correctly while keeping track of the depth. After defining the helper function, we initialize the root of the BST with the first value in the order list, structured as a list containing the value itself and placeholders for the left and right children. We also initialize max_depth to 0 to keep track of the maximum depth encountered during the insertions. Then, for each subsequent value in the order list, we call the helper function to insert the value into the tree and calculate its depth. After each insertion, we update max_depth to ensure it always holds the maximum depth recorded so far. Finally, after all values have been inserted into the binary search tree and their respective depths calculated, we return the max_depth variable. This value represents the maximum depth of the BST that was constructed based on the given insertion order. By using this approach, we ensure that the algorithm efficiently calculates the depth while adhering to the properties of a binary search tree. Here, we begin by defining the solution class and creating the method maxDepthBST, which calculates the maximum depth of a binary search tree given the insertion order. Inside this method, we define a nested tree node class to represent each node in the BST. Each node stores its value and has references to its left and right children, both of which are initially set to null. Next, we implement the helper function insert_n_get_depth, which takes the root node and a value to insert. This function traverses the tree, comparing the value to be inserted with the current node's value. If the value is less than the current node's value, we move to the left child. If the left child is null, we create a new node as the left child, increment the depth, and return it. Otherwise, we continue down the left subtree. Similarly, if the value is greater or equal, we handle insertion in the right subtree, which we'll see shortly. In this continuation of the insert_n_get_depth function, we handle the case where the value needs to be inserted into the right subtree. If the right child of the current node is null, we create a new node as the right child, increment the depth, and return it. Otherwise, we move to the right child and continue traversing. The depth counter is increment at each level of the tree as we move down. After defining this helper function, we address an edge case where the input array is empty. If the array is null or has no elements, we return 0, since the depth of an empty tree is 0. Next, we initialize the root of the BST using the first value in the array and set the initial maximum depth to 0. Then, we iterate through the rest of the array, inserting each value into the tree using the insert_n_get_depth function. After each insertion, we update the maximum depth by comparing the depth of the current insertion with the current maximum depth. Finally, we return the maximum depth. In the main method, we create an instance of the solution class and define an example input array 2, 1, 4, 3. This array represents the insertion order for the binary search tree. We then call the maxDepthBST method with this input and print the result to the console. The output will be the maximum depth of the BST constructed from the given insertion order. This allows us to test the implementation and verify its correctness. By running this code, we can observe how the tree is built and ensure that the depth calculation matches our expectations. This approach is efficient and provides a clear way to compute the depth of a BST based on the insertion sequence. Here, we start with the insertion order 10, 5, 15, 2, 1. Initially, the root of the binary search tree, or BST, is set to 10, and its left and right children are both null. The maximum depth, which tracks the deepest level of the tree, is initialized to 0. The first insertion is the value 5. Since 5 is less than 10, we move to the left child of the root. The left child is currently null, so we insert 5 there. This makes the tree structure 10, 5, none, none, none. The depth of this insertion is 1, so we update the maximum depth to the greater of the current depth and the previous maximum, which is now 1. Next, we insert the value 15. Starting at the root, 15 is greater than 10, so we move to the right child of the root. The right child is currently null, so 15 is inserted as the right child of 10. The tree now looks like 10, 5, none, none, 15, none, none. The depth of this insertion is 1, so the maximum depth remains 1. Then, we insert the value 2. Starting again at the root, 2 is less than 10, so we go to the left child, which is 5. From there, 2 is less than 5, so we move to the left child of 5. Since this position is null, we insert 2 here, making the tree 10, 5, 2, none, 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 15, none, none. The depth of this insertion is 2, so the maximum depth is updated to 2. Finally, we insert the value 1. Starting at the root, 1 is less than 10, so we move to the left child, which is 5. Then, 1 is less than 5, so we move to its left child, which is 2. Comparing again, 1 is less than 2, so we go to the left child of 2. The position is null, so we insert 1 here, creating the final tree structure, 10, 5, 2, 1, none, 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 15, none, none. The depth of this insertion is 3, and we update the maximum depth to 3. With no more values to insert, the final output for the depth of the BST is 3. In this example, the insertion order is 8, 3, 10, 1, 6, 14, 4, 7. Initially, the root of the BST is set to 8, and the maximum depth starts at 0. The first value to insert is 3. Since 3 is less than 8, we move to the left child, which is null, and insert 3 there. The depth of this insertion is 1, so we update the maximum depth to 1. Next, we insert 10. Starting at the root, 10 is greater than 8, so we move to the right child. This position is null, so 10 is inserted as the right child of 8. The depth of this insertion is also 1, so the maximum depth remains 1. The next value to insert is 1. Starting at the root, 1 is less than 8, so we move to the left child, which is 3. Since 1 is less than 3, we go to the left child of 3. The position is null, so we insert 1 as the left child of 3. The depth of this insertion is 2, so we update the maximum depth to 2. Then, we insert 6. Starting at the root, 6 is less than 8, so we move to the left child, which is 3. This time, 6 is greater than 3, so we move to the right child of 3. The position is null, so we insert 6 as the right child of 3. The depth of this insertion is also 2, so the maximum depth remains 2. Next, we insert 14. Starting at the root, 14 is greater than 8, so we move to the right child, which is 10. Continuing, 14 is greater than 10, so we go to the right child of 10. The position is null, so we insert 14 as the right child of 10. The depth of this insertion is 2, so the maximum depth remains 2. Then, we insert 4. Starting at the root, 4 is less than 8, so we move to the left child, which is 3. From there, 4 is greater than 3, so we move to the right child, which is 6. Finally, 4 is less than 6, so we move to the left child of 6. The position is null, so we insert 4 as the left child of 6. The depth of this insertion is 3, so we update the maximum depth to 3. The final value to insert is 7. Starting at the root, 7 is less than 8, so we move to the left child, which is 3. Then, 7 is greater than 3, so we go to the right child, which is 6. Next, 7 is greater than 6, so we move to the right child of 6. The position is null, so we insert 7 as the right child of 6. The depth of this insertion is 3, so the maximum depth remains 3. With all values inserted, the final output for the depth of the BST is 3. In the last example, the insertion order contains only one element, 1. Here, the root of the BST is simply set to 1, and its left and right children are null. Since there are no additional values to insert, the tree remains as 1, none, none. The maximum depth does not increase and remains at 0. Therefore, the final output for the depth of the BST is 0. To analyze the time complexity of this algorithm, let's start with the insertion process. When we insert a value into the binary search tree, we traverse from the root to the correct position for that value. The number of comparisons and movements during this traversal depends on the current depth of the tree. In the best-case scenario, the tree remains balanced, and its depth is proportional to O log n. This means each insertion takes O log n, and inserting all n elements results in a total time complexity of O n asterisk log n. On the other hand, in the worst-case scenario where the tree becomes skewed, such as with sorted input, the depth grows to O n. Here, each insertion takes O n, and inserting all n elements results in O n superscript 2. For the average case, when the input order is random, the tree is expected to be approximately balanced, so the depth remains O log n, leading again to O n asterisk log n. Additionally, updating the maximum depth during each insertion is a constant time operation, contributing O1 per insertion or O n in total. When we combine these, the overall time complexity is O n asterisk log n in the best and average cases, while the worst case is O n superscript 2. Now, for the space complexity, the primary factor is the memory required to store the binary search tree. Each node in the tree consists of 3 elements: the value, the left child, and the right child. Since each node occupies a fixed amount of space, the total space requirement for n nodes is O n. Next, because the algorithm uses an iterative approach for insertion, there is no additional stack space needed for recursion. This means the stack space usage is O1. Lastly, there are a few auxiliary variables, such as the root, max_depth, and depth, which also consume a constant amount of space, O1. Adding these together, the overall space complexity of the algorithm is dominated by the BST storage, resulting in O n. When comparing this approach to a brute force method, the differences become clear. A naive strategy might involve inserting each value into a list and then sorting the list to simulate the structure of a binary search tree. This would be highly inefficient, as sorting after each insertion leads to a time complexity of O n superscript 2, for both insertion and depth calculation in the worst case. In contrast, the current optimized approach avoids such redundant operations by directly constructing the BST while tracking the depth. This reduces the time complexity to O n asterisk log n in the best and average cases, which is a significant improvement. To justify the big O analysis mathematically, the insertion cost depends on the tree's depth. For a balanced tree, the depth is O log n, so n insertions take O n asterisk log n. For a skewed tree, the depth is O n, leading to O n superscript 2. As for space complexity, each node in the BST stores a fixed size structure, and with n nodes, the total space usage is O n. This makes the algorithm efficient for random or nearly balanced input orders, though it performs less favorably with highly skewed inputs. When working with the depth of a binary search tree, it's important to watch out for several common mistakes. One of the most frequent errors involves confusing the depth of the tree with the number of nodes. Remember, depth refers to the length of the longest path from the root node down to a leaf, not the total count of nodes in the tree. Additionally, it's crucial to be mindful of the type of tree representation you're using. If you construct a binary search tree without balancing it, such as with an AVL tree or a red-black tree, you risk creating a highly skewed structure, especially when the input is sorted or nearly sorted. This can drastically inflate the depth of the tree. Another common issue arises when the impact of insertion order is misunderstood. The sequence in which elements are inserted directly determines the structure of the tree. For example, if the input is already sorted, the resulting tree can become degenerate, resembling a linked list. Finally, edge cases should never be overlooked. Scenarios like an empty input array, which results in a depth of 0, or a single element array, where the depth is 1, need to be handled explicitly. Errors can also arise during the actual depth calculation, such as forgetting to traverse both left and right subtrees or failing to correctly return the maximum depth between them, which can lead to inaccurate results. Understanding the nuances of this problem is critical, especially in an interview setting. Interviewers often use it to assess your grasp of binary search tree properties and how the order of insertion affects the tree's structure. You'll want to articulate why certain insertion sequences lead to deeper or more unbalanced trees. Beyond solving the problem, discussing optimization strategies can set you apart. For instance, mentioning balanced BSTs like AVL or red-black trees demonstrates your awareness of how to minimize depth systematically. Another way to stand out is by addressing edge cases. Showing that you've considered scenarios like empty arrays or single-element arrays highlights your attention to detail, a quality interviewers highly value. Additionally, understanding the time complexity of BST operations is essential. Insertions in an unbalanced BST have a worst-case complexity of O(n) due to the tree's potential height. However, balanced BSTs reduce this to O log n, which is much more efficient. Being able to explain these trade-offs and their impact on performance can leave a strong impression in an interview. This problem is closely related to several other LeetCode challenges, which can help you deepen your understanding of binary search trees and their applications. For example, LeetCode 98, Validate Binary Search Tree, tests your ability to recognize and enforce BST properties. LeetCode 108, Convert Sorted Array to Binary Search Tree, focuses on creating a balanced BST, which ties directly into the concept of minimizing depth. LeetCode 701, Insert into a Binary Search Tree, deals with the mechanics of insertion, making it a great complement to this problem. Finally, LeetCode 104, Maximum Depth of Binary Tree, offers practice in depth calculation, though it applies to general binary trees rather than just BSTs. In terms of alternative approaches, you could use recursive insertion while tracking depth. This method is simple to implement but can become inefficient in the case of unbalanced trees, where the depth might reach O(n) in the worst case. A more sophisticated option is to use balanced BSTs like AVL or red-black trees. These ensure that the tree remains balanced during insertions, keeping the depth at O log n. The trade-off, of course, is the increased complexity of implementation. Lastly, an iterative approach can be used to simulate recursive calls with a stack or queue. This method avoids recursion limits but may be trickier to implement cleanly. Each approach has its strengths and trade-offs, and understanding these can help you choose the most suitable one for your needs. Great job following along. To summarize, we learned how to calculate the depth of a BST from its insertion order, discussed the iterative approach, and reviewed key insights about tree structure and properties. If you enjoyed this tutorial, please like, subscribe, and share. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!